Okay, Chem 7, welcome to the fourth video review for the common exam. This is supercritical material, supercritical. And today's topic will be periodic trends. Periodic trends. All right, remember with me, we focus in terms of groups on the periodic table. We use the system which gives us the valence electrons and the effective nuclear charge directly. So this would be group 1A here, group 2A, and then we skip across. So we have 3A, 4A where carbon is, 5A where we find nitrogen and phosphorus, 6A oxygen and sulfur. Key elements, and then 7A here for the halogens, fluorine, chlorine, bromine, and iodine, which I'm not showing you here. I'll just extend the square, right? This would be I right here, iodine, all right? And then group 8A here for the noble gases. Make sure going into the common exam, which is 2 questions, that you are comfortable enough with the periodic table to either know the groups the way they have them numbered here, 1 through 18, or that you also understand the group numbers done the way that I did here, where these are the main group elements. That's where the A comes from, and in the numbering system excludes the transition metals, which are here in the middle. All right, periodic trends. We have 2 of them that I'm going to discuss here. The first is going to be the atomic radius or size. Let me put them down. Let's see, actually I'm not going to do it that way. So periodic trends, atomic radius and size, and ionization energy. So let's talk about, when you look at the periodic table, let's just make a list of the things that are observable. The first is that the atomic number of the elements increases left to right. And I'm just going to abbreviate it this way, left to right. All right, and that should be obvious to you. We go from hydrogen, for example, to helium. The atomic number of hydrogen is 1, helium is 2. Then if you come back over here on the left, we start in period 2 with lithium, which has an atomic number of 3, and we finish with neon, which has an atomic number of 10. So atomic number increases left to right. Why does that matter? Some of you are going to look at this and just think, oh, well, this is something I can memorize or whatever. Well, why would you memorize something that is common sense? But beyond that, what does this mean? It means that the nuclear charge in the atom is increasing left to right. That's what it means. And that means the force pulling on outer electrons, i.e. valence, increases left to right. Remember, the valence determines the size of the atom. Where the valence is, that's your surface. The valence is the surface of the atom. Okay, number 2. So atomic radius is the technical term for it. I like to characterize this as just calling it the size of the atom because it's easier for people to understand. All right, and this is going to decrease left to right. Now, for those of you that are thinking at this point and using your brain, it should be obvious why the size of the atom is decreasing left to right. It's because the atomic number is increasing. It's because as you go left to right, the nuclear charge in the atom is going up, and that means that there's more force pulling on the outer surface electrons, which are the valence, and that's going to cause the valence to be pulled in closer to the nucleus. thereby causing those particular atoms to be smaller than the ones on the left. So fluorine is a smaller element compared to lithium. Neon is smaller than lithium, and so on, going left to right. Okay, moving down any group. I'm just going to move that in here closer, down the group. Okay, moving down the group, size increases. Now, at first glance, if you look at the atomic numbers, like let's take group 8A here, and we start out with helium that has an atomic number of 2, and we end up with krypton has an atomic number of 36. And you go, well, Dr. Pete, why doesn't it work the same way going down the group? Well, you need to remember that the reason the size is increasing, the main reason, the main we go to the market reason is because each new valence, as we move down, is in a bigger N number or energy level. Okay, if that blew your doors off and you're sitting here going, I don't get it, then pay attention right now. We got helium is in period number 1, and then we have period number 2, and then we have period number 3, and krypton would be in period number 4. So you need to remember what period number is. Let's go ahead and we will define it right here. Period number. This is equal to the energy level of the valence. Yes, indeed, the energy level of the valence. And you can see as you go down from helium that each time we move down, the valence has moved out to a completely new energy level. So from neon to argon, the valence is going from a placement of energy level 2 to a placement of energy level 3. And then argon to krypton is moving from energy level 3 to energy level 4. So the distance of the valence is increasing. Distance valence is increasing down the group, which doesn't happen when we're talking about going left to right. Does not happen going left to right. Does not happen going left to right. Going down any group, each new element has had its valence move to a more distant energy level. Okay, number 3. In number 3, we're going to deal with ionization energy. Now, if you think about what we've been talking about, you should actually be able to figure this trend out without me having to tell you what it is. Or if you bothered to study earlier in the year, then you would know already. Ionization energy, all right? I'm going to go ahead and put the definition up here so I have room to work. So the IE, this is the energy required. I'm going to abbreviate that to remove an electron. Energy required to remove an electron. Let's keep it simple, people. All right, now think about it. Let me put my period numbering over here on the left side so we have it in both places. All right, so if you think about moving across period number 2 from lithium to neon, you can see that the nuclear charge, the atomic number is increased, the nuclear charge is increased. And what did we say about that? The nuclear charge is pulling harder on the valence electrons of the elements that are on the right side of the table compared to the ones on the left. So logic follows from that it's going to be easier to remove an electron from an element that's on the left side of the table than it is to remove an electron on the right side of the table. So going left to right, your ionization energy increases. It's harder to remove an electron from neon than it is from lithium, all right? It's pretty straightforward. And then down any group, all right? I shouldn't have to go through the whole thing again that we did here in number 2. All right, down any group. As we move down the group, each new element has its valence in a brand new energy level, which is further away from the nucleus. Further away from the nucleus. So down any group, ionization energy decreases. Okay, and with that, I'm going to go ahead and close the video.